Welcome. The lectures until now have discussed many forces and some moments. For instance, stability and control. The last lecture we looked at the moments, especially the pitching moment, but we also saw different types of controls. And one of those controls was the thrust force. And that is the topic of today, propulsion, the basic principles of propulsion and how this thrust force is generated. Remember that one of the first lectures we showed this picture where we have the view of all the different groups on the aircraft, and every group had its own view. And today it's time for the propulsion group, so their view dominates today. And you might be surprised that this aircraft actually does exist. It's the GB. It's a racing aircraft for air races around two poles. And well, there they optimized their design in terms of propulsion. And this resulted in this aircraft, which is basically a flying engine with little wings. Dangerous aircraft as well, in terms of handling qualities. The previous lecture would not have been very favorable on this aircraft, because if you reduce speed, it's and you end up close to stall speed, it's very dangerous, unable to recover. But today we will look at this engine and the jet engine as well, and look at the basic principles. If we look at the history of engines, it was the Wright brothers again who were the pioneers. They required a certain type of engine for their Wright flyer, and so what they did is basically they wrote a letter to all engine manufacturers, and they specified the weight and power requirements that they had. And the engine manufacturers replied to them that this model that they requested was not available. And also that physically speaking, even if they made some improvements, no, it wasn't possible to make this type of engine with such amount of power for such a limited weight. And this is where the Wright brothers showed their character, because many would have given up there and probably have spent the rest of their lives building gliders. But they didn't. They said, okay, if the engine manufacturers can't make it, it means we have to make it ourselves. So they designed this engine with the following specifications. That the amount of power, it varies. If you look at the model that is preserved and the calculations that we did and what is written in historical literature, let's say it's somewhere in between 12 or 20 horsepower. It used water cooling, and the weight was 150 pounds, as you can see, though with fuel it's actually 50 pounds more. And this was their overall requirement. They required a certain weight of fuel plus the engine, which had to last a certain amount of time, only a few minutes. So this was their requirement, and they built it themselves. They weren't experts on this, they weren't engine manufacturers, but they had the luxury of owning a bicycle factory. And so they had some possibility to make this at least, but it wasn't their expertise, so they were able to do this, and it's quite an achievement for those pioneers. Another pioneering age was, of course, the invention of the jet age. And when the gas turbine was proposed, again, the experts, in this time it was the Gas Turbine Committee in the US National Academy of Sciences had this gas turbine committee in which all experts on gas turbines were united. And gas turbines were then mainly aimed at applications on the ground. So when considering this for airplane propulsion, they made this remark, which says, even considering the improvements possible, the gas turbine could hardly be considered a feasible application to airplanes, mainly because of the difficulty with the stringent weight requirements. Now be aware that to every jet engine today on an airplane is a gas turbine. So these experts thought it was too heavy, even with all the improvements possible. And of course, if you look at the timing, they said this in 1940. Actually, it was 2 years before already that there were experiments with a jet engine on aircraft in Germany. So this shows that you have to be skeptical sometimes even when experts say something, especially when they say something is not possible. And it also reminds me of what you hear today often on electrical propulsion. There you will also hear that it's of course not possible to apply this onto larger aircraft, but we see it being applied on ever larger aircraft. First only the toy airplanes, UAVs, and then we see the first private airplanes with electrical propulsion. So we have to wait and see if electrical propulsion ever becomes a possibility. Well, for any propulsion, there are a number of physical principles which we will discuss in this lecture, and this will allow you to answer some basic questions on engines, on propulsion. For instance, why would you choose a jet or a propeller engine? Or why are modern jet engines as large as they are? Why they are so big? Because the older jet engines were much smaller. And also, how can you improve the efficiency of a jet engine? What do you need to do for that? And therefore today we will look at the basic principles of propulsion and look at this thrust force, the forces, the green forces on the right we already discussed, the lift and drag and the aerodynamics, and weight, how to minimize weight in the structures lectures. And today we'll have a closer look at how the thrust force is generated. It's important to realize that the airspeed of the aircraft, from the engine perspective, if the engine is your frame of reference, then this speed is also the speed with which the air enters the engine or the propeller. And therefore this is often indicated with the symbol V0. So that's the speed with which the air enters the engine or the propeller. And this V0 is used as a starting value. But that only refers to the standard airspeed of the aircraft, the true airspeed of the aircraft. Well, the principle that we use for propulsion for aircraft is what is called reaction propulsion. This means that we increase the speed of the air around us, and this reaction force is our thrust force. It's comparable with a water rocket. Maybe you've once as a kid or later have built a water rocket, and this shows some basic principles which we will later encounter in our physical or more mathematical discussion of how propulsion is generated. A water rocket is basically a bottle which is halfway filled with water, but above it there's air, and by attaching a little valve to the bottle with the cork, so the only work you really have to do to build a water rocket is basically to attach this valve to a cork, and then you can increase the pressure of the air above the water. And this way you store energy in the water bottle, in the water rocket. As soon as you then release the cork, then the water is expelled, and this creates a reaction force, and this launches the water rocket. Well, the principles that we see here is basically shown by the two components of our propulsion system here. We have the water, which is needed because you need a certain amount of mass to accelerate to create this reaction force. And water is 1,000 times heavier than air. The problem, however, with fluids is that they hardly can be compressed. So that's why you also need air to store the energy, which will then generate the extra speed of the water. And so the combination of a lot of mass and a lot of speed creates a very effective propulsion system. And the water rocket is basically a dangerous toy. If you launch it, you better make sure that your head is not above the water bottle, because it can really accelerate very fast, and it's in that sense it's a dangerous toy. You have to be careful with it if you're going to try this at home. But the two principles, mass and speed, mass flow and extra speed, is what we will also encounter when we look at the principles of propulsion. So let's have a look at this with our engine as a reference frame. So here we see an engine, an air-breathing engine as we call it, because there is a certain amount of air that goes in. And there we have a speed. The entry speed is the true airspeed of the aircraft, V0. And the mass which enters the engine is indicated by the mass flow. That's the amount of mass that enters the engine per second. So kilogram per second is m dot or m flux is the mass flow. What the engine then does is that it accelerates this amount of air and creates a higher speed at the exhaust, which is the jet speed. In case of a jet engine, that we be aware that the same principles go for a propeller engine, which also accelerates the incoming air. Now, the difference between those speeds, the fact that the speed is higher when it leaves the engine, creates the thrust force. In physics, the principle can be explained by using the concept of momentum. Momentum is what is basically the product of mass times velocity, is the amount of momentum that the airflow or anything has. And in fact, if you look at the second law of Newton, which you might remember as mass times acceleration, you have to be aware that originally Newton phrased it differently. He said the force is equal to the change of momentum. In other words, the change of the product of mass and velocity. And if we take the derivative to time of this product using the chain rule, we get mass times the change of speed per time unit, or the change of mass per time unit times the speed. And of course, most of the times, the mass of what we're looking at doesn't change, which means that you're only left with the first term, which says mass times change of speed, the rate of change of speed, and that is mass times acceleration. But in a way, it is a simplification of Newton's law, which states that it is the change of momentum. Well, if we apply this to our situation, the change of momentum is basically the mass flow times the speed change, the change in the difference between the speed, the jet speed, and the starting speed of the air. And the mass flow here is not the change of mass, but we see that the units are similar, that we see here kilogram per second times meter per second, which is the same as the product of mass and acceleration. It results in kilogram times meter per second squared. So in terms of units, it also fits, but this is simply the change of momentum of the airflow when it goes through the engine. Well, this is the basis for the formula which we will use a lot in this lecture, and that is that the thrust is created by this mass flow and the speed change. In other words, T is m dot times the jet speed minus the starting speed of the air, Vj minus V0. And this is the first basic equation which we have to remember. It's our primary result, is this equation for the thrust. And remember our water rocket, and you see the same two principles here. We see the mass flow, and we see the speed indicated by the second part of this equation. And be aware that even though in these drawings we use the jet engine, the same goes for the propeller engine. It's simply then the amount of the speed change between the air before it enters the propeller surface and when it leaves the engine, or the propeller surface. So this is the basic principle for any air-breathing engine, any engine that uses the reaction propulsion that accelerates the air to create a thrust force. If you look how this energy is created, you basically look at all the different engine types, and there are different ways to get the propeller rotating or to power a gas turbine, and it has to do with for instance, the energy source which you choose. It is today even possible to create a human-powered airplane. It has crossed the channel, the albatross you see here, where if you're a very lightweight but very strong athlete, then the human body, even though it's a very weak engine, it can generate enough energy to fly, apparently. Well, we see currently a rise of electric propulsion, especially on small aircraft. And there is also on the other side of the spectrum the rocket propulsion, which is mainly used in experimental or emergency situations or flight tests. But most of the engines that we see today are called air-breathing engines, in the sense that they also use the oxygen from the air to generate energy, to burn fuel. And then how this is transferred into a thrust force, well, there are two different ways to do this. There's the propeller and the jet, but that's apart from the physical principles of the engine, which are the same for both propeller and jet engine. So this physical principle of how an engine works is what we will look at in the next video clip.